Good day everyone. In this video we are going to talk about the electron configuration and orbital diagram. So an electron configuration tells us the placement of electrons in the atomic orbital. So for example, the electron configuration of neon is 1s2, 2s2, and 2p6. And this term tells us the energy level, the type of orbital, and the number of electrons. So we need to follow rules and principles to construct the right electron configuration and orbital diagram. We have the affable principle, and this tells us that electrons occupy the lowest possible energy. The Hans rule tells us that electrons fill the orbital one at a time, and the Pauli exclusion principle tells us that no two electrons in the same suborbital has the same spin. And so this is the correct way of depicting our electrons in the suborbital. And this figure tells us the path of energy levels, and this is now the correct way of filling our suborbitals with electrons. And so I'll come up with 3 steps to construct our electron configuration and orbital diagram of any element. Number 1 is to find the atomic number. Second is to construct the configuration following the affable rule, and we need to stop if the exponent's sum is equal to the atomic number. Third is we need to construct the orbital diagram while taking note of the Pauli exclusion principle and the Hans rule. This table will be our guide for the number of suborbital and number of electrons in the orbitals. The suborbitals in the orbital diagram are usually depicted as doors or windows like this. Let's try to find the electron configuration and the orbital diagram of chlorine. Chlorine has 17 electrons, and so our exponents should sum up to 17. So following our build-up, let's start with 1s, and it can hold the 2 electrons. So we need to add some more until we reach 17. Following the path, we have 2s2. Next, we have 2p, and it can hold up to 6 electrons. Next in the configuration is 3s, and it can hold 2 electrons. So we have 12. And we only need 5 to complete our configuration. The next in the path is 3p, and we only need to put 5. Because if we put 6, that would be another element. And this is the final electron configuration of chlorine. For its orbital diagram, we need to follow the Pauli exclusion principle and the Hans rule. For the 1s orbital, I can readily write this. So I'm going to write the spins up first and then the down spin electron. Same for 2s. And this is different for the case of 2p because we need to fill the suborbitals one electron at a time. So let's start with the spin ups first, followed by the spin down electrons. And that's completing our suborbitals. So in the 3s, for the 3p, we need to count the electrons since we only need 5, and we have to stop here. For krypton, following the same build-up, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. For its orbital diagram, it has something that looks like this. For the titanium element, it has 22 electrons. And its electron configuration is like this. To add the exponents, you have 2 plus 2, that's 4, plus 6, that's 10, plus 2, 12, plus 6, 18, plus 2, 20, and another 2, we have 22 electrons. So that's correct. So we only need to look at the atomic number, and we need to match that with our exponents. And so the orbital diagram of titanium is something like this. And that's it, guys. In this video, we talk about electron configuration, the Pauli exclusion and the affable principle, and the Hans rule, and finally we determine the full electron configuration and orbital diagram of the elements chlorine, krypton, and titanium. So thank you so much for listening. I hope that you learned something in this video. Mega bless us all.